Okay, so let's take a look. Anybody have any question, concern, any problems? Okay, then let's continue. This is a very simple lab again. What we're gonna do, we're gonna take a look how the resistors circuits look like. So if I connect, let's say, resistor symbol is this wiggly line, right? Zigzag shaped line, and then the two end corners like the horizontal, that's a resistor. Okay, so if I connect resistors serially, let's say R1, R2, and another resistor R3, so into a circuit, so these two resistors will act like a single resistor. That gonna be, we usually call it R equivalent. EQ means the equivalent resistance or the net resistance, you can say. So that equivalent resistance is addition of all these resistors together, R1, R2, and then R3, and then so on. If you have more serially connected, serial mean one after the other, okay, same line. That's the idea of serial. Serial mean on the same line, different items connected together, okay. One item here, another item here, another item here, and then so on. You can connect any in the same line. That's a serial connection. So if you do that, resultant will be addition of all of those together, okay? And if I connect parallelly means if I have a resistor here, and then let's connect the resistor number 2 just below that, and then resistor number 3 after that. And then let's connect the voltage supply outside somewhere here. So that's going to be the voltage supply. This is the switch and the battery. Let's say VB, let's see is R1, R2, and then R3. So this is a parallel connection. Reason why it is a parallel connection, if you have a current coming from here, this is positive side of the battery, negative side of the battery. So the current goes from positive to negative. So this current, when it reach this junction right here, you can see it's a T, like the T junction, right? So the current gonna be subdivided into two sections, right? So then I have a current I1 on the top line, current I2 on the second line, current I3 on the third line. So which means if you look at it, this circuit via these two endpoints A, B, all of these resistors has the same voltage endpoint A, B. However, the current is different. So such a connection we usually call the parallel connection. Okay. So that's the idea of parallel. Voltage is same, but the current is different, okay, for the parallel connection. And if you compare that concept with the serial connection, since it is on the same line, current gonna be same, but the voltage will be divided into sections, okay. That's the idea of serial. Current gonna be the same, but the voltage gonna be different between each component. So if I have this kind of connection, then if I consider the total or the effective resistance of all of those three, let's consider there's a one resistance going to be equivalent to all those resistance values together. So that resultant resistance going to be inverse addition of each resistance, R1 plus R2 plus R3, parentheses negative power 1. Which means if you adding resistors parallel to each other more and more, resultant resistance or the equivalent resistance going to be less and less because it's inverse addition. Okay, that's the idea. That's the concept and the theory and the principle what we need. Two formulas and the principles and the theory background on that. Then let's take a look, just create couple of circuit and then take a look this concept, okay? And then we can confirm that by looking into the circuit. That's the plan. Any question? Okay, so then let's continue. Let's start with the lab manual. You can download the lab manual and then it should have a simulator link on page number 4. right here. So if you click on that, we used this link earlier, it's same simulator. Okay, all right, so that simulator I think familiar to everyone now. Left hand side you have a couple of options: battery, bulbs, resistors, switch and wires, and then so on. And the right hand side you have a current and the labels, values, and the voltmeter and ammeter. And advanced option we don't need. We need the wires with the resistance very low, and the battery resistance we need 0. So just keep it as it is. Don't change anything on the advanced option. Okay. And then let's create couple of circuit. Okay, we'll start with the most simple circuit: two resistors serially connecting together. So we'll pick two numbers. Okay, so I'm gonna pick 15.5 ohms. Ohms symbol is right here. If you can't find it, you can just copy paste from there on the table. Okay. So the ohm symbol is actually the resistance, and the R2, let's do 25.0. Okay. It can be any numbers, doesn't matter technically, but I'm going to pick those two. Then R equivalent going to be addition of those two, right? 25 plus 15.5, that's going to be zero point 0.5, and then 5 plus 5, 0, and 2 plus 2, 4, right? So it should be then 45.5, right? Good. Any question? 40.5, sorry. And also the unit ohms. And that's our equivalent resistance we expecting from the formula, right? From the theoretical equation. So the equivalent resistance mean addition of these two directly because resistors are in series, right? So let's connect a circuit and then try to figure out that by using the Ohm's law principle. Okay, so that's what we're trying to do on this table. Let's build the circuit. So I need the resistors. I need two resistors. Okay, so resistor number 1, and I need another resistor number 2. Let's connect those two by using a small wire piece, and then we need a battery. Battery voltage doesn't matter, just leave it like that. And we need the switch. Okay, and then we need the ammeter to measure the current passing through the resistors. Let's connect it here. And then we need the voltmeter to check it out the voltage across this circuit. Okay, that's the plan. And let's connect this circuit other two endpoints by using the wires, and another wire here. Now the circuit is connected. Now I have to select the resistor values correctly according to my table. Resistor number 1, if you click on that, the slider will appear down here. So I need the 15.5, okay, resistor number 1. So that's the number we decided earlier. 15.5, resistor number 2, we need about 20.0, okay, 20.0, 25.0, right, 25.0. You can click and drag or just click on the arrows. Okay, either way is fine. So make sure you pick these two numbers, 15.5 and 25.0. And that's our circuit now. Circuit is properly adjusted. This should be 15.5, not 6. Okay. And then we have a 9-volt battery. Doesn't matter the voltage, just leave it like that. That's a standard battery we can use in the lab setting too. And the current right now zeros because the switch is on brake position. I have to put the switch on, then only it can be, current can be flow through, right? If you do one click on the switch, it will close. You can see now electron is moving. So now you can see the current value here. Okay, that the same current pass through this line because of that both resistors has the same current. Okay, now what we're going to do, so we know in theory if I add these two resistors we should get about 40.5. total resistance. Now what we're going to try to do, we're going to try to figure out by using the Ohm's law. Okay, so what we have, two resistors connected serially, resistor 1 R1, resistor 2 R2, and then we have a battery and then switch and the ammeter. And that's our circuit. Right now, if I use the voltmeter and then measure the voltage across these two directly, that's going to be the voltage across both of these resistors. Okay, and then if I measure the current through here, then if I apply the Ohm's law to this whole circuit, okay, Ohm's law means V equal IR. When I apply that, R should be equal V divided by I. This V is voltage across both resistors. Current is the passing current throughout the circuit, both resistors. Because of that, if you apply the Ohm's law, resistance value we calculating here gonna be the effective or the net or the equivalent resistance on this circuit. So that should be exactly the theoretical value we calculated earlier by using this formula, about 40.5. That's the plan. Okay, so we'll test it out now. In that way we can actually test two different concept and principle. We can test it out actually validity of the Ohm's law itself, and also we can test it out the resultant or the equivalent resistance of the resistor circuit which is connected serially. That's the plan. Any question? Any problems? No? Okay, then let's continue. Then let's measure the voltage across this circuit. So we need the voltage across both the resistors, total voltage, right? So that voltage actually directly this voltage, because you know this end connected to the negative of the battery. This end is actually directly connected to the ammeter, but nothing in between, all our wires. It's look like this end is connect directly here, right? So it's going to be about 9 volt. So now let's take a look by using the current and voltage, whether I can get the same answer, right? So that's next step. Any question? Let's take a picture also, because since you're planning on writing a lab report for this one, all of these circuit diagrams, you should put it with the table in your data section. Uh, or if you want, you can put all of those diagrams into the procedure section, nothing wrong, but it is better to have those circuit diagram with the table. Okay, so we'll collect those circuit diagrams, all of these places. Insert illustration screenshot. I think you guys know how to do this now. So I need this circuit with the voltmeter included. I think that's better. Let's leave it here. And then let's do the calculation. Voltage across both resistors are 9 volt. And if you measure two decimal places, if you see two decimal places in your instrument, you should record that. Okay. So which means I have to increase number of decimal places in this cell. So I can do that by using the number area right here on the top, home menu, and by using the left arrow. Okay, so we need two decimals for that. Current is 0.22. That's two decimal places again. So the equivalent resistance by using the Ohm's law equals sine voltage divided by the current. Okay, about 40.9. We expecting it's 40.5 in our theory. We're getting slightly off reading. The reason I purposely selected the R1 15.5. When I'm measuring the current specifically, you can see it cut down from the second decimal place. That is one reason why we see a little bit of error. That's totally fine. Okay. And also we don't need this many significant figures, decimal places. Okay, we'll get rid of those decimal places and then leave only two decimal places. Okay, not more than two. one decimal place more than what we can directly calculate in terms of significant figure point of view. Okay, and that's it. Then we'll compare these two numbers because this is what we experimentally observed. This is what theoretically or in terms of principal point of view what we expecting. So let's compare those two. Equal ABS parentheses theoretically expected value 40.5 minus calculated value is on cell number D14 close bracket divide by 40.5 multiplied by 100. So our percent error also very low, about 1%. Also get rid of the decimal places. Keep only two decimals, okay, not more than two. Let me copy paste these two commands just below the table right here. So this is going to be our, we can say equivalent calculated, and that's going to be the percentage different. Okay guys, any question? We do percentage error relative to the theoretical value, not the difference. Okay. All right, any question? Okay, then let's continue. So that confirm the resistor connection serially, and also it in a way confirm the Ohm's law too. And let's take a look now parallel circuit. So parallel circuit means voltage should be same, current must be different. Okay, now you can see that's a serial circuit, current is same, and the voltage is dividing between these two within the with the applied voltage right here. Okay, it's 9 volt, but if you measure across each resistance, those are different numbers, right? Across resistor 1 you see about 3.44, across resistor 2 you see about 5.56. If you add them together, then you will get 9 volt. Okay, that's the idea of serial connection. Same line, different voltage, but the same current. Now let's build the parallel one. Okay, I'm going to keep this one here. Let's build the parallel one in here. Then you can get an idea how the parallel circuit and the serial circuit look like. Okay, so let's keep the same previous circuit. Let's build a new one. I need again the battery, we need the ammeter, and we need this switch between the battery and ammeter. And these two now should connect parallel to each other to the same endpoint. So I'm going to make it this way, then we can clearly see both resistor. This left end is connected to one point, and the right end also we can do the same way, then we can see it clearly connected to the another one single point. Let's keep the same values of resistances. First one 15.5. If you click on the resistor, that's the yellow line appear, then you can change the resistor values. Okay, since you use this simulator earlier, I think those are familiar to everyone. If not, always ask. Okay, 15.5, and then the second resistor will do the same number 25. Okay, we can get a better idea how the same resistors, if I connected serially, I'm going to get a larger value. If I connected parallelly, it's the inverse addition, I should get a smaller value. Okay, that's the idea. And let's complete the circuit. I need the one wire here connected to this end. I need another wire here connected to this end. There's no current yet. Reason the switch is off position. Let's put the switch on. Then you can see each of the resistors have the current separated out. We can test it out that also. If I break here, Let's put the two ammeters separately, then you can see actually the current values are different. Okay, let's put two ammeters here to check out that one. Okay, now you can clearly see that's our parallel circuit. So the two ammeters in each segment has a different numbers. The top one has 0.58, lower resistance, higher the current. Bottom one has 0.36, higher the resistance, lower the current. Okay. If you add those two currents together, then the outer line, this one, has a total current. That's the resultant current. Okay. But if you measure the voltage now across each of these resistors, we'll put between these two endpoints, each of these resistors has the same voltage because both endpoints are connected to the battery directly. That's the idea of parallel connection. Okay. Any question? Okay, now you can see the difference. Okay, what's the how the serial to parallel is changes. Okay, now let's we can take a picture of this one too, and then let's continue to next part. Let's take a picture of that one and then place it here. Two resistors connected parallelly. Insert illustration screenshot. And we need only parallel circuit right here. I think if I get this part, that's only we need. Okay, I'm going to get only that part because if I try to get the voltmeter, I'm going to get the part of the other circuit too. That's good enough because we interested only the circuit itself. So I think that's fine. And let's take a look how the calculation look like now. Any question?
Yeah, hold on, Professor. I need to see how you did that.
Circuit?
Yeah,
Okay, right here.
I'm trying to figure out how you did that. You connected those three wires. And I'm sorry, this is just like confusing. It's kind of hard to use this thing. It's like not working.
Got it?
Yeah, it's like my thing's like not working.
Your circuit is not working. That's
No, it just like the
simulator is not working.
yeah, it's like it's kind of glitching out. Hold on.
Try to refresh the whole page, the
Yeah,
web
I'm
page.
trying to figure it out again.
Yeah, sometime it can happen, and also if the internet issues can happen.
Hold on. Okay, I think I'm getting it.
Working now.
I believe so. Wait, hold on. I'm just getting different numbers than you.
Then you have to check resistance values first.
Let's make it 15.5.
First one 15.5, second one 25.
Okay, thank you.
And the voltage should be fine because it automatically select 9 volt. Just keep that. If you have all of those same, I think you should get the same numbers as what we see here.
Yeah. All right, I'm getting it. Thank you.
Okay. Yeah. Anyone else has any problem? Okay, then let's continue now. We took the picture earlier. Okay, so we can use that. We have the information on the picture too. We can use that here R1. It's the same numbers actually. You can copy those two numbers from the previous if you want to, from the previous table. We're going to use the same two numbers. Now equivalent is inverse addition. Okay, if I have this kind of connection, so the effective resistance going to be inverse 1 over R1 plus 1 over R2 parentheses minus power 1. Okay, so let's write that formula in our Excel. Then we can find the answer easily. Okay. If I want to do it in Excel, I should do that outside here. Okay. because right here I have this word. I can't leave the answer with the word itself. So I'm going to calculate it outside somewhere here. Let's put our equivalent and then equal. Let's put the function here next cell, okay? Equal sign, parentheses, another parentheses, 1 divided by 15.5, close brackets, plus parentheses, 1 divided by 25, close bracket again, power, shift and number 6 is the power, hat sign, and minus 1, and then hit enter. Now you can see that number is very different than any other numbers we did. Okay, so this is the command equivalent for this particular case. Just calculate in that previous cell right here on the top. Okay. Now, if I add the resistors parallelly, you can see the same numbers we are using like the previous, but the effective or the resultant value now less because it's inverse addition. Okay, that's the idea. And let's add that number here theoretically, or the concept point of view, the expected value going to be now 9.56. 9 point, we can round that into 57, and ohm sign you can copy paste from the previous table or from here. Okay, that's the expected value, right, in theory. Let's take a look by using the Ohm's law whether we can get the same answer, right? That's the plan. Now to do that, we can consider the whole these two resistors are acting like a single resistance. That's the resistance what we call the Req. Now if that is connected to this voltage, same voltage, then I can use the Ohm's law, right? So the voltage across this, and if I know the current from the ammeter, then we can use V equal IR again, same way we done earlier. From that, we can recalculate Req. That will be the experimental value. Total voltage divided by the total current passing through the total resistance. Okay. So let's take a look at that angle. The total voltage we measured earlier. You can go and take a look. 9 volt between both the resistances. And 9.00. If zeros are not showing up, make sure you add 2 decimal places by using the home menu, numbers in the middle, little small blue arrow to the leftward direction twice. Okay. And the current passing through the both of them is actually the outer number right here. Outside you see this number, that's the current passing through the both of them, right? 0.94. That's the one we interested, because we interested total circuit, not the individual segment. Okay, it's gonna be 0.94. So let's calculate the resultant or the effective resistance by using the Ohm's law. Equal sign voltage divided by the current. Okay, so we getting about 9.5744. We expecting 9.57 in previously, about 9.57. It's about the same. We can cut down the decimal places on this calculated value also after second one. No meaning keeping more than 2 decimal places. Okay. Let me copy paste that function also, maybe here. It's going to be then R EQ. I'm going to use by using Ohm's law. Okay. By using Ohm's. Okay. Question. All right, then let's compare them together. Calculated value and the measured value from the Ohm's law. Okay, equal sign, ABS, open brackets, uh, equation point of view, calculated value 9.57 minus experimentally measured values on this cell D number 25, close brackets, divide by 9.57 multiplied by 100. Very, very small. The reason it's almost very perfectly close numbers. Okay, about 0.5 percentage error. I think again 2 decimal place is enough. No meaning keeping more decimal places there. Let's copy paste that command into here. Okay, guys, any question? Okay, so that is that simple. Nothing serious or nothing any difficult calculation or anything. I think should be fine. But if you have any question, always ask. Anybody have any trouble doing the calculation? Any of them? Good. Okay, then let's take a look combined circuit, right? So the circuit not necessarily like only serial or only parallel, right? If you look at the real circuit diagram, there are so many combination of serial and parallel. It's very complicated circuits in general, right? Let's try to connect two circuits series and then the one resistor parallel to that, which means we can make a circuit look like this. So we can put two resistors series to each other. This way, let's say R1 and R2. Then R3 will put parallel to those two. So our circuit gonna be look like this then, okay? Then our external voltage supply should be connected to these two ends because the effective gonna be the effective of those three. The first two connected serially. So that's going to be directly adding those two together. Now this and this parallel connection, which means the equivalent resistance of this one should be equal parentheses 1 divided by R1 plus R2 because those two serial, but it is connected parallel with R3 close brackets negative power 1. Because if you look at it point A and B, this resultant resistance from outside point of view looks parallel. Okay, these two should be connect parallelly. That's why inverse addition. Now let's decide the number for R3. Let's do R3 about like maybe 35 ohms. Okay, we'll keep the R1, R2 same. Let's add the new resistor and then let's try to find it out what will be the equivalent resistance of this circuit. Now this is a combination of serial plus parallel. Okay, that's the idea. Any question? Okay, then let's take a look first the circuit diagram. You can get rid of all of these now. We don't need. Just if you click on this yellow, this circle on the right hand side bottom corner, so that's a reset button, everything will disappear. And then let's bring the two resistors, one resistor, second resistor, and then the third resistor parallel to that. Okay, and then let's bring two wires, few wires, and then first connect these two ends together because I need first two serially, the third one parallel to that. Let's connect these two ends also together. And then let's bring the battery, let's bring the switch, and also we need the ammeter to measure the current. Okay, and let's connect these endpoints with another few wire pieces. Now that's our circuit. So our circuit has two resistors serially on the top, one resistor parallelly on the bottom, right? Now let's do a couple of adjustments because we have to select the resistor values, right? Click on the first one, select 15.5. We're going to keep the same number for R1 as we done earlier. Resistor number 2, we're going to keep the same 25 ohms. Okay, 25 ohms. Resistor number 3, we're going to pick 35 ohms. Okay, doesn't matter those numbers actually, but for consistency, use exactly these numbers. Okay, then all of us going to get the same answers. 35.0. Now let's take a look the same idea, right? In theory, we know the formula how to get the resultant. In Ohm's law, what I need is the voltage across these two endpoints. That's where I need the voltage. And then I can find the total current passing through here in this ammeter, right? If you switch on, you will see the current now 0.48 and the total voltage across whole circuit is 9 volt. By knowing those two numbers, we can calculate by using Ohm's law equivalent resistance, and also we can calculate the same number by using the expected value by using the equation we discussed earlier. Okay, any question? Okay, that's our table number 3. So let's do a picture here. Insert illustration, screenshot, screen clipping. We can take a picture on this resistor circuit, including the voltmeter, and we'll add that into here, around here, and let's do these numbers first. Resistor 1 and 2, it's the same values, right? I can actually bring the numbers from the previous if you want to, nothing wrong because we keep in the same numbers, right? Resistor 1 15.5, resistor 2 25.0, and resistor 3. Actually, you can do this too. This is maybe useful if you click on the values on right hand side top, all the numbers showing up, that will be useful to have. Okay, so take the picture including those numbers, because if you want to check that later when you're writing a report or something, then it is useful. Then we know what values of resistance are in which place in our circuit diagram. That will be very useful information. Okay, so we'll keep those numbers visible. Okay guys, any question? Resistor number 3, then 35.0. Resistor number 3, sorry, R3 equal 35.0, and the unit ohm you can copy paste from the previous cell. That will be the easiest. Then let's calculate. Now in terms of calculating, we can do that calculation here, somewhere below here. And you know the formula we discussed earlier, these two adding together, and then this one adding parallel to that. So it's going to be 1 over R1 plus R2 parentheses plus 1 over R3, another parenthesis outside, negative power 1. Okay, that's the equation we would like to use to calculate this number. Let's do that calculation here. Req equals, so let's do that in the next cell, equal sign, parentheses, another parenthesis, 1 divided by another parenthesis, 15.5 plus 25, close brackets again, plus parentheses 1 over 35, close brackets again, power hat sign minus 1. Okay. Now you can see that number is very different from any of the previous values. Okay, so that's the idea. So because in generally you can't buy every single resistance values from the market, then we need actually different way of creating the values we need in certain applications. So that's why these resistor connections are very useful in various way when you build in the circuits. Okay, let me copy paste that command right here, req. So that's the function we use, okay, right here. And let's now take a look what's the number from the Ohm's law point of view, right? So we're expecting about 18.77, right? So that's what we're expecting. The unit you can copy paste from the previous cell. Any question? You have to write that function very carefully. There's a lot of parentheses. If any mistake will give you a wrong answer, okay? And let's continue then. Let's take a look the same.
Can you copy and paste that into the chat?
Oh, this command.
Yeah.
Oh, yeah. Let me do that. Uh, yeah, so right there. Okay, any other question? Check that function carefully, okay, because it has a lot of parentheses. If any mistake, then we're going to get a wrong answer there. And let's take a look now the same in terms of Ohm's law point of view. If I do the Ohm's law for this one across these two endpoints, right, these two endpoints, then we have the voltage 9.0 and the total current passing through is that number, right? So 0.48. So by using Ohm's law, we can figure out the resistance equivalent should be equal then V over I. Let's calculate by using these two numbers. Okay. So let's take a look at then. Voltage gonna be 9.00. Zeros are not visible always. You can add zeros in the home menu bar. Numbers, 2 clicks on the right is small blue arrow. Okay. Current 0.48. Let's calculate the Ohm's law point of view. What should be the equivalent resistance? Equal voltage divided by the current. So then hit enter. About 18.75. We have a little bit of error, but almost it's the same. Okay, so let me copy paste that also to somewhere here. Maybe it's gonna be our equivalent. I'm gonna put ohms there. Okay, it means Ohm's law point of view. Okay, questions. All right, then let's compare those two like we done earlier. Equal sign, expected value 18.77, ABS, open brackets 18.77 minus experimental value is the Ohm's law point of view answer on D number 37, close brackets, divide by expected value 18.77 multiplied by 100. It's a very small percentage error. Get rid of any unnecessary decimal places. Keep about 2 decimal places. Okay, we don't need more than 2. So this is going to be then percentage error for this case. Okay, guys, any question? Let's get rid of the probably. Okay, guys, any question? Anybody have any problems doing that calculation? Good, no problem. Okay, then let's continue to next one. So next one we're gonna connect another circuit. In that circuit, we still keep the serial parallel combination, but we'll change how we connect the three resistors. Okay, we'll keep the same values of the resistors too, these three values, but we'll do two in parallelly and then one in serially. Okay, so which means we can connect that circuit. Let's connect two first parallel to each other. These two, let's put parallel, R1 and R2. Let's put R3 serial to that. These two now parallel to each other. And then the voltage gonna be from outside and the switch. Then if you look at this circuit now, these two are parallel, so that resultant should be 1 over R1 plus 1 over R2 parentheses negative power 1. That's the resultant from R1 and R2. R3 should be directly added into that because totally these two are serially connected in the same line. See, that's the idea, right? So then this should be now equivalent resistance. You can see how the formula changes from one to other. It's the same three resistance, but the previous one and then this one is very different from each other. Okay. So again, the same thing. Let's calculate the expected value from this formula. Then we'll measure the voltage across these two endpoints. That's a 9 volt. We'll figure out the current by using the ammeter. Then we'll figure out the R equivalent by using the Ohm's law. That's the plan. Okay. Any question? Good. No questions? Okay. Then let's continue. All right. So let's build that circuit first. Okay. So to do that, let's get rid of this circuit and then let's build from the scratch that is here. Okay. So I'm gonna bring resistor 1 right here, and then I'm gonna bring another resistor. Let's first these two in parallel to each other, right? R1 and R2, like this one. R1 and R2 parallel now. Then let's bring the third resistor, put serial to each other. Let's bring a battery. Let's bring a switch, and then I need an ammeter. Then these two endpoints should go to our circuit resistor connections like this. Okay, that's our new circuit. Now let's take a look how these values are, because I need resistor R1 15.5, right? I'd like to keep the same numbers like we done earlier. And resistor R2 about 25, and then resistor R3 about 35. Okay, because then we can compare and then get an idea how the previous circuit changes compared to this one. Okay, 35, this one. Okay, any question? All right, then I just need to close the switch and also click the values. Okay, that always useful because when you're making the report, you need all those information, right? So we need the voltmeter. We would like to measure the voltage across total circuit right here. So that must be 9 volt because outside voltage directly 9 volt battery, and the current you can see now very different any of the previous. It's just 0.2 amps. Okay guys, any question? Okay, then let's continue. All right, so let's take a look. Table number 4. R1, R2, R3 values are same. You can actually copy paste these three numbers directly into next table. And they are equivalent, we built a formula earlier. Let's do that calculation here, right? Let's bring the circuit diagram first here. Insert pictures, screenshot, screen clipping, and let's take a picture of this whole circuit, including the voltmeter. And you don't need really large pictures, just resize the picture into a like reasonably small size, okay? And then let's do the calculation. This we again going to do it somewhere here under the table. R equivalent equal, let's write the function in next line, next cell. Equal sign, parentheses, another parentheses, 1 over R1 15.5 plus parentheses 1 over R2 25, close brackets, power minus 1 plus R3 just 35. Okay, so that's the number now we expecting in this circuit. You can see it's the same three resistors, but previously it was 1877. Now it is 4456. So it's a very different because the resistor connections are very different. Okay.
Can you paste that in the chat box, please?
Oh, sure. Yeah.
Thank you.
So let me copy paste that function in here. Okay, then let's do that calculation. Okay, the function is on the chat box if you want to use that. Let's let me copy paste that down here to R equivalent. Okay, now let's do that calculation. We're expecting about 44.57, right? 44.57. Let's do units from the previous cell into here. Then we have the unit also. Let's do in terms of Ohm's law point of view. Volt is 9 volt. Again, you may have to change the number of sig figs there on the volt cell to about 2 decimal places. Current now is 0.20. So that also makes your second decimal place is visible. From Ohm's law point of view, resistance equivalent going to be voltage over current. About 45, we expecting 44.57. That's very close numbers. Also, you can keep 2 decimal place on there. Okay, only 2, not more than that. Then let's compare. So this is gonna be then how we got the R equivalent from Ohm's law point of view. And let's compare those two numbers. Equal sign, ABS, expected value 44.57 minus Ohm's law value is D47 on that cell, divide by 44.57 multiplied by 100. So change the number of decimal places to only 2. Percentage error you can see less than 1, so that's very, very good number. Right here. Okay guys, any question? That's our table 5, table 4. Let's take a look now, table 5. 2 more tables to go. That's fairly very quick. Any question? Okay, table 5, actually we already done all different type of circuits. So in table 5 and 6, what we're going to do instead of resistances, let's connect light bulbs. And then we'll take a look how the light bulbs intensity or the illumination changes if you connect serially and parallelly to the same voltage. And then in your lab manual has a couple of questions attached to those two tables. If you go right here, this part is optional, so I skip that one, we don't need to do. But this one, part 5 is the one we're going to do on table 5. Part 6 is the one on table 6. Okay, so it asking couple of questions how the light bulb illumination look like, things like that. You can answer that on your report, okay, when you make in the report. For table submission, you don't need to do answers for those. Completing the table is enough. But for lab report, when you do the discussion part, just discuss about those things, okay? It's just what you observe technically. Okay, guys, any question? Okay, let's get rid of everything on this page by clicking this yellow circle on the right hand side bottom corner. Instead of resistors, now let's bring the bulb. Okay, let's connect 3 light bulbs serial to each other. Okay, one after the other. So this goes to the outside. This piece connected together, then this connected together, the outside connector. Let's bring the battery. Let's bring a switch. Let's bring an ammeter. And then let's connect these two endpoints. And then put the switch on. So all the light bulbs are illuminating. Then the light bulb actually has a resistance value. Okay, so if you click on each of the light bulb, its resistance show up here. It's about 10 ohms. We can keep as it is. We don't need to change that number. Just keep the 10 ohms. That's okay. Okay, and let's now take a look. Voltage across light bulb, we know if you measure total voltage, that's going to be the same value as the external voltage, right? 9 volts, so we don't need to measure that either. We can get rid of that. Now let's take a look on table number 3. We'll do the same calculation by using the Ohm's law point of view here in the table. But in your report discussion, answer the question asking about how the illumination look like, whether each light bulb is the same illumination or different, things like that. And then answer those things in discussion, okay? So R1, R2 light bulb 1, 10 ohms, 10.0 ohms. We can copy paste the ohm symbol maybe from here to here. And then the 10 ohm value is actually same for all 3 light bulbs. Let's put that copy paste into next 2 cells. Okay, light bulb 3 also the same value. Now you know, if I have a light bulb is the resistor itself, right? If I have a 3 light bulbs connected together serially in the same line, resultant should be direct addition, right? Let's put the values also on. So the equivalent mean the direct addition, this should be then 30 ohms, right? So that's the number we expecting. We can check it out that by using the Ohm's law point of view, right? So let's take a picture first, insert, screenshot the screen clipping, and then this whole circuit into right here in table figure 5 area. And then on table 5, voltage across the all 3 light bulbs 9 volt. Again, make sure you increase the number of decimal places to 2. Current passing through the circuit point 3, increase decimal places to 2. Equivalent resistance mean equal sign voltage over the current. It's about 30 ohms. We're getting exact answer because we're using a very round values now. 10.0, 10.0, 10.0. That's why we're getting exact answer there, okay? So I will write it down here, R equivalent from Ohm's law point of view. Oh, that is our experimental value actually in a way. Increase the number of decimal places to 2 to make sure that really 30.0, and then PE gonna be 0. Actually, we don't need to even do that. The reason the both expected value from the formula and the measured or the Ohm's law value is exactly the same. Okay. Any question? Okay, then let's do another one last check. by putting the same light bulbs, but now let's connect them parallel to each other. Okay, so I'm gonna reset this whole thing and
Professor, I have a question.
yeah, what's up?
Why is the percent there zero?
Because these two numbers are exactly the same, are equivalent from the formula and they are equivalent from the Ohm's law. See that?
Wait, oh, I
That's
didn't get the formula. Hold on. What's the formula for it?
these are equivalent right here. That's going to be R1 plus R2 plus R3. Let me write it down that here. R1 plus R2 plus R3. Okay. So
Do we
if you
have to
add these
include that?
two, 10 plus 10 plus 10, then you will get 30.
I
Okay.
mean, do we have to include that though? Do we have to like put the formula somewhere?
Right here, I just add into here R1 plus R2 plus R3. Since it is just 10 plus 10 plus 10, we don't need to write the function or anything. I just put that R1 plus R2 plus R3. Nothing much to do there. Okay. And then from the Ohm's law equation right here, just under the table. Okay. That's the equation I use here for cell number D59. Since those two are same, I actually did not write a percentage equation for this one, ABS equation, because it's not meaningful. We comparing 30 and 30, you're going to get 0 anyway. I just put 0 there. Nothing to do, nothing to calculate actually.
Okay. Okay. I was just making sure I didn't miss something.
Okay, yeah. Okay, guys. Then any other question?
Professor,
Yeah, what's up?
can you copy and paste actually the formulas for the REQ for table 1 and 2? Because I didn't get them.
Oh
Sorry.
yeah.
Thank you.
R equivalent, which we use right here. Yeah. So, oh, this one. This is just direct addition. I actually didn't use the equation for the
Oh, you just
table
did
one.
direct addition?
Yeah, it just direct addition. That's why I did not
Okay. And
even
what about for
write
table
it.
2?
Table two is inverse addition. That let me copy paste that one. That's right here. So that will be inverse addition. It should be this one. That for table two. Okay. Table one, it just direct addition.
Thank you so much.
Yeah. Okay, guys. Any other question? Let's then check it out. Last table. So we'll reset this one, bring three light bulb. Let's connect three light bulbs parallel to each other. So which means each should go top of each other, right? Like that one. So all the light bulbs, one end should be connected together. All of these end will put it together. All of these end will put it together right here. And all the other ends will put it together into one point. I put it light bulb little bit separated out from each other because it's otherwise you're not going to see it clearly. Okay. Now let's put a battery. Let's put a switch here. Let's put the ammeter also. And also let's click the values to see all the light bulb values, resistance values, and then let's connect these two endpoints. Then we have our parallel circuit now. Three light bulbs together. Okay. Now let's switch on and then we'll see now how it look like. Okay, now that's the question it asking on the lab manual, how this illumination looks compared to the previous. Okay, you can just look at the uh, picture and then answer that literally. You don't need anything else to specifically, but you can get an idea by looking at the current, for example. Okay, if you look at the previous picture, total current passing through is zero point 0.3. Now total current passing through is 2.7. So each segment has now more current than actually previous. So the illumination is too higher. Okay, so let's take a picture into this. That will be useful also during your report. This whole part. Make sure the values are visible, then it is actually very useful during the report. If you have some question, you don't need to rebuild the circuit, you can just check the picture and then understand what really went on. Okay, and the R1, R2, R3 values are exactly the same as earlier. Each light bulb is 10 ohms. However, now it is parallelly connected, so which mean I have to do inverse addition for this one, right? Let's do right here. R equivalent equal next cell equal sign parentheses another parentheses 1 over 10 plus another parentheses 1 over 10 plus another parentheses 1 close bracket plus another parentheses 1 over
Please
10.
put that in the chat box. Sorry.
Sure. And power sign minus 1. Since it is 1 over addition, you can see it is a very small number now, right? So that's the idea. Always parallel connection will give you a lower resistance value. So our expected value going to be now about 3.33. Okay. Since our resistance, effective resistance is smaller, that's why the circuit actually has larger current, right? Resistance is smaller, mean the lot of current pass through. So the illumination, if you look at the diagrams, much higher now. Okay. Let's do Ohm's law point of view. The voltage is 9 between the all of them, right? Each of them are connected to the same endpoint. Make sure 2 decimal places. Current 2.70, 2 decimal places. Resistance from the Ohm's law point of view, just the ratio of voltage and current. Okay, about the same number exactly. We can get rid of the decimal places. We'll keep only 2. Since it is exactly the same, there's no meaning doing the percentage error. We'll just put 0 there. Okay. If the numbers are at least some little bit different, we should do it. But since it is same, no meaning doing it. Okay. And let me copy paste this function under the table right here. R equivalent calculated value directly. And also let me copy paste the Ohm's law equation right below that. That's gonna be R equivalent from Ohm's law point of view. We're gonna put just ohms there, okay? And that will be the experimental value technically, okay? That's the idea. And other important thing, when you connecting the circuit, light bulb usually connected parallelly. The reason, if you have the serial connection, if one light bulb goes away, then the other light bulb also not going to work because it's serially connected. The whole circuit going to break down. But if it is a parallel, one light bulb goes away, burn out, then other light bulb is still going to work. Okay, that's how the home circuit actually built. A light bulb must be parallelly connected to the circuit. One does not affected to the other. Okay, that's the idea. So that's about it. Any question?
Thank you.
All right, guys. So we can stop here. You're supposed to write a lab report for this one. Make sure you check the lab sample lab report and then follow that structure and everything. And the lab report submission link will open up by March 5 because I'm gonna delay that one until you finish the data sheet. Okay, data sheet must submit just by tomorrow midnight. Okay. All right, guys. So we'll stop here. If you have any question, stay on the call. Otherwise, I will see you guys next week.
Professor,
What's
is
up?
the lab report due the 17th of this month?
This one?
Yes.
Yeah, you usually have 2 weeks for lab report. Yeah.
Okay, thank you.
Yeah. Yeah.
Have a good night.
Yeah.
Professor,
What's up?
I have a problem